Welcome to this problem-solving session. Today, we'll be tackling the problem titled Duplicate Zeros, where we explore an array manipulation challenge. Get ready to dive in as we break down the problem and approach it step by step. Let's get started. This problem is all about handling zeros in a fixed-length integer array. Specifically, whenever we encounter a zero in the array, we need to duplicate it by shifting the subsequent elements to the right. However, there's an important constraint. Since the array has a fixed length, any elements that go beyond the original array length as a result of these shifts are simply ignored. Additionally, the modifications must be done in place, meaning we don't create a new array or return anything. This means our solution needs to directly manipulate the input array. Let's look at an example to understand this better. The input array is 1, 0, 2, 3, 0, 4, 5, 0. The process begins by duplicating the first 0 at index 1. This shifts the elements to the right, resulting in 1, 0, 0, 2, 3, 0, 4, 5. Next, the 0 at index 4 is duplicated, and the array becomes 1, 0, 0, 2, 3, 0, 0, 4. Finally, the 0 at index 7 is ignored since it lies beyond the array's fixed length. The final modified array is 1, 0, 0, 2, 3, 0, 0, 4. This demonstrates how zeros are duplicated in place while adhering to the length constraint. Now, consider the input array 1, 2, 3. Here, there are no zeros in the array. Without any zeros to duplicate, no modifications are made, and the array remains unchanged as 1, 2, 3. This shows a straightforward case where the input and output are the same since the duplication logic isn't triggered. Next, we have another example to explore a different scenario. In this case, the input array is 0, 0, 0, 0, 0, 0, 0, which consists entirely of zeros. If we attempt to duplicate each zero, we quickly run into the length limitation of the array. Starting from the first 0, we duplicate as many zeros as possible until the array is completely filled. The final result remains 0, 0, 0, 0, 0, 0, 0, as no additional zeros can be added beyond the fixed length of the array. This demonstrates how the length constraint influences the outcome when there are many zeros. Now, let's summarize some important constraints and edge cases. The array length is guaranteed to be between 1 and 10,000. And each element in the array ranges from 0 to 9. This means our solution needs to handle potentially large arrays efficiently. Key edge cases include arrays with no zeros, where no changes are made, arrays with all zeros, which result in maximum shifts, and arrays where zeros appear only at the end, as these zeros cannot be duplicated within the fixed length. For large arrays, it's crucial to ensure the solution adheres to the in-place modification requirement while remaining performant. To solve the problem of duplicating zeros in an array, we considered multiple approaches. The first and simplest is the brute force method. Here, the idea is to iterate through the array, and each time we encounter a zero, we shift all the subsequent elements one position to the right and insert an additional zero at the current position. This ensures that every zero is duplicated correctly. However, the main downside is the repeated shifting of elements, which becomes computationally expensive as the array grows larger. The time complexity for this method is n squared, because for every zero, we might end up shifting a large portion of the array multiple times. On the other hand, it has a space complexity of 1, since we modify the array directly without using additional storage. While simple to implement, this approach struggles with efficiency, especially for larger input sizes, due to the repeated shifting of elements. To address the inefficiency of the brute force method, we use a more optimized solution called the two-pass strategy. This approach avoids repeated shifts by first determining the number of zeros that need to be duplicated using a single pass through the array. Once we know how many zeros to duplicate, we can calculate the effective new length of the array, accounting for these duplicates. In the second pass, we work backward from the end of the array and copy elements to their new positions. When we encounter a zero during this backward traversal, we duplicate it by writing two zeros at the appropriate positions. This ensures that no elements are overwritten prematurely. With this strategy, we process each element at most twice, leading to a time complexity of n. Additionally, it requires no extra memory, as all modifications are done in place, giving it a space complexity of O1. By avoiding redundant shifts, this method is much faster and more efficient than the brute force approach, especially for larger arrays. An alternative solution involves using a queue to simulate the process of duplicating zeros. In this approach, each element is pushed into the queue as we iterate through the array. When a zero is encountered, it is duplicated by pushing 2 zeros into the queue. Once all elements have been processed, the array is reconstructed using values from the queue, stopping once its original length is restored. While this method is simpler to understand and implement, it uses additional memory, as the queue requires O(n) extra space. This violates the problem's in-place constraint, making it less desirable. Ultimately, the two-pass strategy stands out as the best choice for this problem. It strikes the perfect balance between efficiency and memory usage, achieving O(n) time complexity and O(1) space complexity. By counting zeros first, it avoids redundant computations, and its backward traversal ensures no premature overwrites. The brute force method, though conceptually simple, is inefficient for large inputs, and the queue-based method, while intuitive, fails to meet the in-place requirement. Therefore, the two-pass strategy provides the most practical and performant solution to duplicate zeros effectively. To solve the problem of duplicating zeros in a fixed-size array, we first need to clearly understand the requirements. Each zero in the array should be duplicated, meaning an additional zero is inserted immediately after the original zero. However, since the array must remain the same size, any elements that extend beyond its bounds are truncated. This introduces a challenge because duplicating a zero shifts all subsequent elements to the right, potentially overwriting data. Instead of shifting elements repeatedly, we can optimize the process using a two-pass solution. First, we count the number of zeros that can be duplicated without exceeding the bounds of the array. Then, we work backward through the array to rewrite its contents, duplicating zeros as needed. This structured approach minimizes unnecessary operations and ensures we meet the problem's constraints efficiently. The two-pass solution begins with a step-by-step plan. In the first step, we initialize a counter, zeros_to_duplicate, to 0. We then traverse the array from left to right, simulating what would happen if we duplicated each zero. During this simulation, we stop counting zeros if duplicating another one would cause the total number of elements to exceed the array's size. Once we know how many zeros can fit, we move to the second step. Here, we rewrite the array in reverse using 2 pointers. The pointer I starts at the last valid index of the original array, while j starts at the last position that accounts for the duplicated zeros. As we move backward, if the current element is a zero, we write it twice to the array provided there's enough space. If it's not a zero, we write it once. Both pointers are decrement as we process each element. This approach ensures we handle zero duplication efficiently while respecting the array's fixed size. Special cases, like arrays with no zeros or ones full of zeros, are handled naturally by this method. For instance, if there are no zeros, the array remains unchanged. If the array is entirely zeros, only the first n zeros are kept. The key to solving this problem efficiently lies in avoiding excessive shifting of elements. Instead of duplicating zeros in place and repeatedly moving all subsequent elements, we calculate in advance how many zeros can be duplicated and adjust the array in reverse. This eliminates unnecessary operations and significantly reduces computational overhead. The fixed-size constraint simplifies memory management since no additional data structures are needed, but it also makes the problem more challenging. Deciding how many zeros to duplicate requires careful planning, which is why the two-pass approach is so effective. The first pass focuses on determining the final arrangement of the array, while the second pass applies these changes systematically. For data structures, we rely entirely on the input array itself, modifying it in place. 2 pointers, I and j, allow us to traverse and overwrite the array efficiently, ensuring the solution remains both space and time optimal. Analyzing the complexity of this solution, we find it highly efficient. The time complexity is O(n), where n is the size of the array. This comes from the fact that we perform 2 linear passes over the array, the first to count how many zeros can be duplicated and the second to rewrite the array in reverse. Both passes are independent and linear, so their combined complexity remains O(n). As for space complexity, it is O(1). The algorithm modifies the input array directly and uses only 2 additional pointers for traversal. No extra data structures are required, making it an in-place solution. This balance of O, N, time and O, 1, space makes the approach both practical and optimal for this type of problem. The solution begins by determining how many zeros need to be duplicated using ARR count, 0. This value is stored in the zeros variable. Since the array size must remain fixed, this count helps manage the in-place modifications without exceeding the array's bounds. Next, the algorithm iterates backwards through the array using a for loop from n1 to 0. This ensures we handle the elements in reverse order, making it easier to shift elements while avoiding overwriting important values. Inside the loop, the condition if I plus zeros n checks if the shifted position, current index I plus the remaining zeros, is within the bounds of the array. If it is, the value at ARR I is copied to its new position, ARR I plus zeros. If the current element is a 0, the zeros count is decrement, as 1 0 is being processed. Additionally, if the duplicated zeros position, I plus zeros, is still within bounds, the 0 is explicitly written to this position. This ensures each 0 is duplicated correctly while respecting the array's fixed size. By processing the array in reverse, the solution avoids overwriting elements that haven't been handled yet. The algorithm operates in O, N, time complexity, as it makes a single pass through the array, and uses O, 1, additional space since all operations are performed in place. Here, we start with a class called solution that contains a method named duplicateZeros. This method takes an array of integers as input and modifies it in place to duplicate each occurrence of 0, while keeping the array's length unchanged. First, we declare a variable zeros to count the number of zeros in the array, and another variable n to store the length of the array. Next, the code uses a for each loop to iterate through the array and count the total number of zeros by simply checking if each element equals 0. Once we know how many zeros are present, we begin another loop that iterates backward through the array. This reverse iteration is key to modifying the array in place without overwriting values prematurely. The condition inside the loop ensures that elements are shifted to their correct positions, accounting for the extra space created by the zeros. Now, as the loop continues, when a 0 is encountered, we decrement the zeros counter and duplicate the 0 in the array by assigning it to the necessary position. This duplication only occurs if the calculated index falls within the bounds of the array, ensuring we don't access out-of-range indices. By iterating backward and shifting elements while duplicating zeros as needed, we achieve the desired transformation of the array in place. This approach maintains efficiency and avoids the use of additional memory, making it optimal for the problem's constraints. To solve the problem of duplicating zeros in an array, we start with the given input, 1, 0, 2, 3, 0, 4, 5, 0. The length of the array is 8, and the number of zeros to be duplicated is calculated as 3 using ARR count, 0. The process involves iterating backward through the array, starting from the last index. At I equals 7, the value is 0, but since I plus zeros equals 10 is out of bounds, we skip this step. Similarly, for I equals 6 and I equals 5, the values 5 and 4 are skipped because their calculated positions, 9 and 8, are also out of bounds. This initial backward traversal helps us identify which elements will be placed within the valid array bounds as we duplicate zeros. Next, at I equals 4, the value is 0. Here, I plus zeros equals 7, which is within bounds. We place a 0 at index 7, then decrement zeros to 2 and place another 0 at index 6, effectively duplicating this 0. The array now looks like 1, 0, 2, 3, 0, 4, 0, 0. Moving to I equals 3, the value is 3, and I plus zeros equals 5. We place 3 at index 5, resulting in 1, 0, 2, 3, 0, 3, 0, 0. At I equals 2, the value is 2, and I plus zeros equals 4. We place 2 at index 4, updating the array to 1, 0, 2, 3, 2, 3, 0, 0. Finally, at I equals 1, the value is 0. Here, I plus zeros equals 3, so we place 0 at index 3, decrement zeros to 1, and place another 0 at index 2, duplicating this 0. The array becomes 1, 0, 0, 0, 2, 3, 0, 0 after this step. At the final step, I equals 0, the value is 1. With I plus zeros equals 1, we place 1 at index 1. The resulting array now looks like 1, 1, 0, 0, 2, 3, 0, 0, but since we are only modifying the original array in place with the same length, the final valid output is 1, 0, 0, 2, 3, 0, 0. This marks the completion of example 1. Now, with example 2, the input array is 0, 1, 0, 2, and the length is 4. The number of zeros to be duplicated is 2. We again process the array backward. At I equals 3, the value is 2, but I plus zeros equals 5 is out of bounds, so no changes are made. Next, at I equals 2, the value is 0. Here, I plus zeros equals 4, which is out of bounds, but we still decrement zeros to 1 and place a 0 at index 3. The array becomes 0, 1, 0, 0. At I equals 1, the value is 1, and I plus zeros equals 2. We place 1 at index 2, resulting in 0, 1, 1, 0. Finally, at I equals 0, the value is 0. Here, I plus zeros equals 1, so we place 0 at index 1, decrement zeros to 0, and place another 0 at index 0, duplicating this 0. The array is now 0, 0, 1, 0, which is the final output for example 2. In example 3, the input array is 1, 2, 3. Since there are no zeros in the array, the count of zeros to be duplicated is 0. In this case, no processing is necessary because there are no zeros to duplicate. The array remains unchanged, so the final output is 1, 2, 3. This demonstrates that the solution handles arrays without zeros efficiently, skipping unnecessary computations. To analyze the time complexity of the solution, we start with the first operation, which is counting the zeros in the array using the ARRCount0 method. This requires iterating through the entire array once, resulting in an O(n) time complexity, where n is the length of the array. Following this, the backward iteration is performed using a for loop that iterates from the end of the array to the beginning. In the worst case, this loop will also execute n times. Within each iteration, there are constant time operations like assignments and conditional checks, which contribute O(1) to each iteration. Since these operations are executed sequentially, we combine their complexities. The counting step contributes O(n), and the backward iteration adds another O(n), giving a total time complexity of O(n) plus O(n) equals O(n). Now, let's look at the space complexity of this solution. The algorithm modifies the input array in place without creating any additional data structures, which means it operates with O(1) auxiliary space. Breaking this down, the solution uses a few auxiliary variables such as zeros to track the number of zeros, n for the length of the array, and I for the loop index. All of these variables require constant space. Importantly, no extra space is allocated that scales with the size of the input array or any other input-dependent factors. This lack of additional memory usage ensures that the overall space complexity remains O(1). Let's consider the best, average, and worst-case scenarios for the algorithm. In the best case, where there are no zeros in the array, the backward iteration still runs n times, but no duplication of zeros occurs. As a result, the time complexity remains O(n). In the average case, with an input containing some zeros, the backward iteration duplicates zeros as needed. However, since the total number of operations is still proportional to n, the time complexity remains O(n). In the worst case, where the array consists entirely of zeros, every element needs to be shifted and duplicated, but because the algorithm operates in place, the time complexity is still O(n). Compared to a naive approach that creates a new array, the given solution is significantly more space efficient. A naive solution would require O(n) additional space for the new array, while this in-place solution achieves O(1) space complexity. When comparing the given solution to the naive approach, the key advantage lies in its space efficiency. While both methods achieve the same O(n) time complexity, the naive approach requires O(n) additional space for the new array, whereas the given solution operates in O(1) space by modifying the array in place. To confirm the time complexity mathematically, we observe that the loop executes exactly n times, and each operation inside the loop is constant time, or O(1). The counting of zeros is also O(n). Combining these, the total time complexity is O(n) plus O(n) equals O(n). Since the algorithm does not use memory proportional to the size of the input, the space complexity is 1. In conclusion, this solution strikes an efficient balance by minimizing space usage while maintaining linear time complexity, making it an optimal choice for in-place array modifications. Here are some common mistakes to watch out for when solving the duplicate zeros problem. First, modifying the array while iterating forward is a frequent pitfall. Since inserting elements like zeros shifts subsequent indices, this can cause elements to be skipped or overwritten. To avoid this, consider using a two-pass or in-place approach that accounts for these shifts. Next, algorithms often fail with multiple consecutive zeros. Duplicating one zero affects the position of the next zero, so it's critical to design your solution to handle such cases, either by pre-calculating shifts or iterating in reverse. Another mistake is relying on extra space, such as creating a new array. While it simplifies the problem, it violates the constraints for in-place solutions, which are often required in these types of questions. Lastly, overcomplicating the solution with excessive nested loops can unnecessarily increase time complexity to n squared. A more efficient approach, such as using two pointers or reverse traversal, can achieve linear time complexity, n, which is far better for larger inputs. Now, let's discuss some additional tips and insights. One common issue is ignoring array bounds. When duplicating elements or shifting values, it's easy to write beyond the array's limits, which leads to runtime errors. Always ensure your algorithm respects the array bounds. For interviews, make sure to test edge cases explicitly. This means handling situations like empty arrays, arrays without zeros, or arrays filled entirely with zeros. Interviewers also tend to favor solutions that achieve n time and 1 space complexity. A good strategy is to first calculate the effective array length after duplications, then work backward to make changes in place. Additionally, if you use extra space for simplicity, acknowledge the trade-off and explain how you'd optimize the solution for in-place constraints. Finally, always think out loud during interviews. Clearly explain your thought process, especially when addressing edge cases or discussing performance optimizations. This showcases not just your solution but how you approach problem solving. Lastly, let's explore related problems and alternative approaches. Similar problems on LeetCode include +1, problem 66, merge sorted array, problem 88, and move zeros, problem 283, alongside duplicate zeros itself. These problems often share concepts like in-place manipulation and handling edge cases, so practicing them can strengthen your understanding. As for alternative approaches, the brute force method is straightforward but inefficient since repeated element shifts result in a time complexity of n squared. While simple, it's not suitable for larger inputs. The two-pointer method is much more efficient, achieving n time and 1 space complexity. However, it requires careful attention to edge cases, like consecutive zeros. Another option is reverse traversal, which avoids overwriting elements during duplication and works well for in-place solutions. While this approach is efficient, some may find it harder to conceptualize initially. Each method has trade-offs, so choose the one that best matches the problem constraints and your familiarity with the technique. Great job completing the duplicate zeros problem. In this session, we explored an efficient two-pass approach to solve the challenge in n time and 1 space. Remember, mastering in-place operations and understanding array traversal are essential skills for coding interviews. Thanks for watching, and don't forget to stay tuned for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!